Imagine you are a network administrator. You're sitting in a coffee shop in Seattle, right?
Right, just having a normal morning.
Exactly. Your laptop is open, you are sipping an espresso, and with, one slightly misguided click on a dashboard.
Oh, no.
Yeah, you accidentally sever the connection to like 100,000 storage drives sitting in a data center halfway across the world in Singapore.
Which is a terrifying scenario, but it happens.
It totally happens. The scope of modern infrastructure is just terrifying. So today we are looking at the exact master blueprint that prevents, or I guess causes, that kind of catastrophe.
Yeah, depending on how you use it.
Right. We're taking a deep dive into the Supermicro SuperCloud Composer. Specifically, we're analyzing the network user guide. This is release 3.11.0, the version from October 2025.
It's a dense manual.
It really is. But I want to be clear for you listening. This isn't about how to plug in a standard router at home. We are dissecting how massive, heterogeneous server farms are managed, how they are automated and diagnosed using a single pane of glass.
And that single pane of glass is critical, because if you've ever wondered how the invisible backbone of our digital economy survives the sheer chaos of constant configuration drift, well, this is your manual.
Yeah, exactly. So why don't you set the stakes for us a bit more? Why does software like this SuperCloud Composer, or SCC as we'll probably call it, why does it even need to exist?
Well, the stakes you just described with the coffee shop scenario are exactly why it exists.
Well,
I mean, we are operating in environments where the physical hardware is so incredibly dense.
like tens of thousands of devices.
Right. And the topology is so complex that human beings just can't manually manage the infrastructure anymore.
You can't just log into each one.
No, exactly. You cannot SSH into 10,000 individual switches to, say, update a routing protocol. It would take weeks. You need an orchestrator.
Right.
And what's fascinating about this document is that it offers this incredibly detailed look at how Supermicro attempts to bridge a very specific gap.
Which gap is that?
The gap between static declarative rules, basically the way we want the network to look in theory, and the highly volatile dynamic memory of the actual network hardware operating at line rate in reality.
Okay, let's unpack this right away. Let's jump into the core of how this system dictates that reality. The manual starts with network provisioning.
The brain of the operation, essentially.
Right. So according to the guide, SCC pushes what it calls build plans to the data switches.
Yeah, build plans.
And the architecture here relies on this Network Configurator wizard. It takes your settings and formats these plans into JSON payloads.
Which is standard.
Yeah, for anyone who manages environments at scale, JSON is the absolute standard, but then those payloads are deployed by a network orchestrator engine via API calls.
Right.
But here's what really struck me. The documentation specifies that SCC can push these plans either single-threaded or multi-threaded for simultaneous updates across the fabric.
Yeah, and that multi-threaded option, that introduces a massive amount of orchestration complexity.
Really? Why is that so much harder?
Well, think about it. If you are pushing a JSON build plan to a single switch, failure is completely isolated.
Okay.
Right, so the API call times out, you get a standard 404 or 500 error, and the orchestrator just flags it. One error, one device.
Simple enough.
But when SCC executes a multi-threaded push to, say, 50 spine switches simultaneously, it has to manage the state of 50 independent asynchronous operations at the exact same time.
Oh, wow.
Yeah, it has to guarantee idempotency.
Okay, wait, for anyone who might not be familiar with idempotency in this context, what does that mean?
It basically means that applying the same operation multiple times has the same result as applying it once. You can retry a failed push without breaking things that already succeeded.
Got it. So if the push fails on switch 22.
Right, but it succeeds on the other 49 switches.
Then what?
The orchestrator needs to know exactly how to roll back or retry that specific node, switch 22, without corrupting the overall fabric topology of the other 49.
It's like managing a synchronized swimming team, and one person starts drowning, but the rest have to keep the routine going perfectly while you rescue the one.
That's a pretty good analogy, actually.
So the manual doesn't just assume these API pushes succeed and remain pristine forever either. And this brings us to a really fascinating feature. The guide introduces something called the switch sweeper.
Yes. The switch sweeper.
I love that name. It sounds like a superhero or maybe a really aggressive janitor. It's an intelligent network agent, right?
Right. Its entire function is configuration compliance.
Which means it constantly compares the original JSON build plan, the desired state, against the dynamic operational memory currently running on the switch.
And the necessity of this switch sweeper really points to a fundamental reality of enterprise networking.
Which is?
Configuration drift is inevitable. It just is.
Configuration drift. Okay, paint a picture for us. How does that happen in real life?
Sure. So you have an emergency at 3 in the morning.
The classic 3 a.m. page.
Yeah, exactly. A Tier 3 engineer wakes up, logs directly into the command line interface, the CLI of a core switch. They bypass the SCC orchestrator entirely because they're in a hurry.
Because things are on fire.
Right. And they manually change a BGP timer to mitigate a routing loop that's bringing down the network.
Okay, so the fix works.
The fix works. The network stabilizes, the engineer's exhausted, so they go back to sleep, and they totally forget to update the central SCC repository.
I see where this is going.
Right. Now, your orchestrator's database is lying to you. The desired state in the central JSON file is officially out of sync with the hardware's operational state.
The blueprint doesn't match the building anymore.
Exactly. Somebody moved a load-bearing wall in the middle of the night and didn't tell the architect.
So the switch sweeper is the building inspector who's constantly walking the halls to see if anyone moved a wall.
That's exactly what it is.
But wait, if the switch sweeper is constantly policing this, how does it physically do it without overwhelming the switch? I mean, if it's aggressively checking for drift on thousands of switches, isn't that generating a massive amount of polling overhead?
It's a huge concern, yeah.
Because you can't just have a central server hammering thousands of switches with requests every 5 seconds, right? The switches would crash just from being asked how they're doing.
Right, and that is the architectural tightrope these systems walk. Now, the manual doesn't explicitly detail the underlying polling protocol line by line, but modern orchestrators like SCC have generally moved away from legacy SNMP polling.
SNMP being the old standard.
Yeah, simple network management protocol. It's incredibly heavy on CPU cycles.
Mm-hmm.
Instead, they rely on event-driven telemetry or very streamlined API querying.
So how would that work in the 3 a.m. scenario?
Well, the switch sweeper is likely subscribing to state changes. When the engineer alters the running configuration, the switch's own operating system registers a state change in its internal database.
So the switch basically raises a flag.
Yeah, it says, hey, something changed. Then the sweeper can just fetch the hash of the current configuration.
A hash being a mathematical summary of the file.
Right, and it compares that hash to the hash of the JSON build plan. If the hashes don't match, it immediately flags the drift. It doesn't need to read every line of code constantly. It just compares the summaries.
Okay, that makes total sense. So it acts as this aggressive auditor enforcing discipline across the compute network. But the guide makes a very sharp pivot right after this.
It really does.
Yeah. When we move from standard network provisioning to storage provisioning, the rules completely change. The rules for compute traffic and the rules for storage traffic are treated as two entirely different paradigms.
And they have to be.
The manual explicitly states that storage switch build plans are constructed using a completely different tool. It's called the Storage Fabric Configurator Wizard.
Right, because standard compute switches and storage switches are often physically identical in many modern deployments.
Wait, really? They are the same boxes?
Yeah, they use the exact same silicon ASICs, the same optical transceivers. The divergence is entirely in the logical configuration applied by SCC.
So why the need for a totally different configuration wizard?
Because storage traffic, particularly in modern data centers, cannot tolerate the standard behavior of Ethernet.
Okay, let's dig into that standard behavior.
Okay.
Because the text specifies these storage plans require additional DCBX parameters for RDMA ROSI-based storage fabrics.
Lots of acronyms there.
So many acronyms. And it explicitly mandates, quote, ETS, flow control and lossless queues to maintain communication between NVMe over fabrics targets and initiators.
Right.
So let's talk about lossy versus lossless.
Mm-hmm.
If we look at standard compute traffic, like an HTTP request for a website or a standard database query, it's inherently lossy, right?
Yes.
If a switch buffer gets congested, it just drops the packet. It essentially throws it on the floor.
And it doesn't care.
Right. And the TCP protocol on the receiving end eventually notices a sequence number is missing, it asks for retransmission, and life goes on. It's resilient. Like a text message, if it fails to send, your phone just tries again.
Exactly.
So why is that resilience, that drop and retry method, completely unacceptable for NVMe over fabric storage traffic? Why is this storage traffic treated like fragile glass?
Because of the latency and the CPU overhead associated with that TCP retransmission. You mentioned RDMA earlier.
Remote direct memory access.
Right. In a traditional TCP/IP stack, when a packet arrives, the network interface card, the NAC,
Mhm.
interrupts the server's CPU.
Okay.
The CPU has to stop what it's doing, process the packet, move it through the kernel stack, and copy it into the application's user space. That takes microseconds, sometimes even milliseconds.
Which in computing time is an eternity.
It's an absolute eternity.
Yeah.
So RDMA bypasses the CPU and the operating system entirely.
Wait, it just skips the CPU.
Totally skips it.
Okay.
The network card writes the incoming data directly into the application's memory space.
Which means it must operate at blistering speeds.
Unbelievable speeds.
Yeah.
We are talking about connecting NVMe flash storage drives across a network and making them perform as if they were physically plugged into the PCIe slot of the local motherboard.
That is wild.
But to achieve that CPU bypass, the protocol assumes a perfectly reliable transport layer. It assumes perfection. So if you drop a packet in a ROCE environment, which stands for RDMA over Converged Ethernet, the entire RDMA connection has to pause.
Because it wasn't expecting an error.
Exactly. It has to rely on a much slower fallback mechanism to request the dropped frame and resequence the data. So a single drop packet can cause a latency spike that literally stalls the entire storage array.
It's like delivering a delicate physical package on a highway at 200 miles an hour. It absolutely cannot be dropped.
Exactly.
Okay, that totally explains the manual's absolute requirement for lossless queues, but here is my question. How do you take standard Ethernet, which you just said is inherently designed to drop packets during congestion, and force it to be lossless?
Yeah, you had to twist Ethernet to do something it wasn't built for.
Right. And the manual lists ETS and flow control as the solution. So how does that work?
It relies on priority-based flow control, or PFC. In a standard older network, if a switch port gets congested, it might send a pause frame. It basically tells the upstream device, hey, stop sending traffic, my buffers are full.
Seems logical.
It is, but it pauses everything on the link. All the traffic stops.
Which is bad.
Right. PFC changes the game. It uses the 802.1q VLAN tag to assign different priorities to different types of traffic on the same physical wire.
Okay, so it segments the single physical cable into virtual lanes, like on a highway.
Exactly like a highway. 8
Okay.
different lanes, specifically.
Wow, 8 lanes.
Yeah. So the storage fabric configurator in SCC is configuring the switch so that ROCE storage traffic is tagged with a specific high priority value, say priority 4. If the switch buffer for that specific lane starts to fill up, the switch sends a PFC pause frame upstream that essentially says, pause priority lane 4, but keep sending traffic on lanes 1, 2, 3, 5, 6, 7, and 8.
Oh, wow. So the standard compute traffic, the lossy HTTP requests, the background telemetry on lane 1 and 2, it just keeps flowing and dropping packets if necessary.
Right.
But the NVMe storage traffic on lane 4 is treated as absolute VIP. The upstream switch stops forwarding those storage frames, holding them safely in its own memory buffers, rather than letting them drop on the floor.
Exactly. It's the ultimate traffic cop. And that is where ETS comes in.
Enhanced transmission selection.
Right. It's not just about pausing when things get full. It's about guaranteed bandwidth. ETS allows the SCC orchestrator to tell the switch, look, no matter how congested the network gets overall, guarantee 50% of this port's physical bandwidth strictly for ROCE traffic.
So it reserves a dedicated VIP lane that can't be encroached on.
Exactly. The orchestrator is heavily modifying the ASIC's physical queuing behavior to create a flawless, lossless subnetwork sitting right on top of a standard, lossy Ethernet infrastructure.
That is incredibly clever. But when you have an environment that volatile, where one dropped packet on a storage queue causes cascading latency spikes and where complex DCBX parameters are defining these virtual priority lanes, how on earth does a human administrator actually visualize that danger?
Yeah, seeing it is half the battle.
Right, which brings us to the SuperCloud Composer's data browser and its physical asset management, because seeing a list of IPs isn't going to tell you where the physical problem is.
No, not at all.
So the manual maps out a very specific navigation hierarchy. You start at the POD level, you drill down to the group, then the rack, then the drawer, and finally down to the specific appliance.
And that hierarchy is vital. The software is deliberately forcing a geographical and physical topology onto the logical data.
Why is that distinction so important for the operator?
In traditional network management, you often just look at a flat list of IP addresses or host names. You sort by red or green status.
Right.
But when you were dealing with power constraints, thermal constraints, or, say, a top-of-rack switch failure, you need to know the blast radius.
The blast radius.
Yeah. If rack 4 loses a power distribution unit, a PCU, a flat IP list, doesn't visually tell you which 60 appliances just died together. But the POD to appliance hierarchy in SCC maps the logical fault domains directly to physical reality. You see exactly what physical rack went dark.
Which saves you so much time during an outage. And when you finally click into a specific appliance, you hit the switch list interface.
Right.
It displays all these data points: switch location, manufacturer, drawer type, SKU, IP address, serial number, and firmware version.
It's a lot of data.
A ton of data. And the manual specifically notes that the search filters apply an A&D condition to all criteria.
Which is an important detail.
Totally. If you're a professional managing thousands of nodes, an A&D filter is non-negotiable. If I need to find a specific firmware vulnerability, I can't just search for the firmware version. I have to search for the vulnerable firmware version and AD the manufacturer to isolate the exact patch group I need to target.
Absolutely.
But there was a UI detail in this section that absolutely fascinated me. It was a specific constraint regarding screen resolution.
Ah, yes. The 1600 pixel threshold.
Yes. The manual explicitly states that the graphical carousel view, which shows, these nice charts for uptime and operational state, it is completely disabled if the user's screen resolution is under 1600 pixels.
It just turns it off.
Yeah. And it also mentions that the software generates a switch schema showing the precise front view and rear view of the hardware down to the 1U drawer heights. But I read that 1600 pixel resolution limit, and my mind immediately went to a technician freezing in the cold aisle of a data center.
Your instinct is spot on. A 1600 pixel width is basically a standard desktop monitor in a comfortable network operations center.
Where someone is sitting with a warm cup of coffee.
Exactly. But if the browser detects a lower resolution, it safely assumes the operator is working under severely constrained conditions.
Like what?
They might be using a KVM over IP console from a decade ago, or they might be balancing a 13-inch laptop on a metal crash cart, physically plugged into the management port of the rack while standing in a 60-degree server room.
Oh man, I've been there. It is not fun.
No, it's not.
And
in those scenarios, you don't have the bandwidth or the screen real estate for fancy graphical carousels displaying uptime charts. You need raw tabular data, and you need it immediately.
So it's a UX decision that actively acknowledges the physical, stressful environment of the user.
Exactly.
And speaking of the physical environment, that front and rear schema view you mentioned, it fundamentally bridges the gap between the software orchestrator and the remote hands technician.
It's so crucial for remote management.
Because if I am in Seattle managing that data center in Singapore, I can't just call the local tech on the floor and tell them to unplug the blue cable on the switch. There are 10,000 blue cables.
And you will definitely take down the wrong database if you say that.
Exactly. But with SCC, I can pull up the rear view schema, look at the exact 1U layout on my screen, and say to the tech, okay, go to rack 4, U-space 32, and pull the transceiver in port 48.
Right. And to generate that specific, accurate visual, the SCC backend is doing some heavy lifting. It has to query hardware-level management APIs, likely something like Redfish or advanced LLDP extensions, just to pull the exact hardware SKI.
Okay.
And then it maps that specific SKI to an internal SVG image library to render the precise physical layout of the chassis on your screen.
Wow.
So it's dynamically translating highly abstracted logical data back into a tangible physical representation for you.
That is just brilliant. But, translating that data is one thing. Manipulating it is a whole different ballgame.
That's where things get dangerous.
Exactly. The manual dedicates significant space to what I would call high-stakes operations: configuration, restarts, and firmware updates. And the language here noticeably shifts. It becomes heavily peppered with these red caution boxes.
The manual gets very serious very quickly.
It does. It outlines that permanent settings must be saved to the startup config, and it warns with a big caution icon that unsaved changes are lost on reset.
Ah, the dichotomy between the running config and the startup config.
Yeah.
It is literally the oldest safety mechanism in networking.
Right, so let's break down the mechanics of that safety mechanism for you listening, because it's so fundamental to how this all works. When an administrator is making changes to a switch through SCC, let's say they are altering a VLAN tag, they are modifying the running configuration. And that config exists purely in the switch's volatile RAM.
Correct. And it takes effect instantly.
Instantly.
The data plane begins forwarding traffic based on that new rule the absolute millisecond you hit enter.
But because it's in RAM, if the switch loses power or if someone issues a restart command, that RAM is completely wiped.
Blank slate.
Right. So the switch boots back up, it looks at its non-volatile memory, its NVRAM for the startup config, and it loads that older version instead. So the manual warning you to save to the startup config is essentially an act of memory preservation. You are committing the current volatile state to the hard drive so it survives a reboot.
That's the standard procedure, yes. But experienced administrators will actually deliberately leverage that volatility to protect themselves.
Wait, how so? Use the volatility as a tool.
Oh, absolutely.
Mm.
If you are sitting in Seattle and you are about to make a highly dangerous routing change to that switch in Singapore, a change that might accidentally cut off your own connection to the switch.
Right, cutting off the branch you're sitting on?
Exactly. You don't save it to the startup config immediately.
Oh.
You apply it only to the running config in RAM. Then, if you make a mistake and accidentally lock yourself out of the switch, you don't panic. You simply call the remote hands technician in Singapore and tell them to physically pull the power plug.
Oh, that is so smart.
The switch reboots, loses the bad running config from RAM, loads the previous known safe startup config from NVRAM, and boom, you regain network access.
It's literally a hardware-level undo button.
Exactly. It's a lifesaver.
That is brilliance. But when you move to firmware updates, that safety net completely vanishes.
Oh, yeah. There's no undoing a bad firmware flash.
The SCC manual says you can upload firmware locally or via the server, and there's a little auto restart checkbox. But a firmware update isn't just changing a rule, it replaces the fundamental operating system, right? It kills both the control plane and the data plane.
It does. It shuts everything down. And this ties right back to the RoCE storage traffic we discussed earlier.
Oh, because of the lossless requirements.
Right. If you restart a switch that is actively handling RoCE storage traffic, you aren't just dropping a few packets. You are completely severing the storage fabric for the entire duration of the boot cycle.
Which can be minutes.
Easily. So unless the network is built with a highly resilient leaf spine topology where traffic can instantly multipath around the rebooting node, a firmware update is a highly destructive action. You have to drain the traffic first.
Which makes a specific detail in the firmware update interface of this manual so incredibly bizarre to me.
The limitation.
Yes. The guide explicitly notes, with a dedicated tooltip icon right in the UI, that this specific firmware update function, quote, only supports Arista switches.
That is a remarkable inclusion for a Supermicro manual.
I found it staggering. I mean, we are looking at the SuperCloud Composer. Supermicro manufactures their own massive line of data center switches. The screenshots throughout the rest of the manual display Supermicro hardware. Yet, the automated firmware flash mechanism from this specific GUI menu explicitly limits itself to Arista Networks hardware. I mean, if you've ever managed a heterogeneous network, you're probably rolling your eyes right now thinking, sure, a single pane of glass works great until you introduce a third-party vendor. But how does SCC actually handle that Arista integration, and why would Supermicro prioritize a competitor here?
It seems counterintuitive, but you really have to look at the enterprise market reality.
Okay, lay it out for us.
Arista completely dominates high-frequency trading and massive-scale data center environments. Their operating system, EOS, is fundamentally built on top of an unmodified Linux kernel, which makes it very robust.
Okay, so they have huge market share.
Huge. But more importantly for SCC, Arista exposed almost every internal state of their switches via eAPI, which is their JSON over HTTP machine interface.
Oh.
And they did this long before many legacy vendors moved away from screen scraping text from CLI outputs.
Oh, so Arista was basically built for API automation from day one.
Exactly. So you're saying Supermicro recognized that if they want SCC to be taken seriously as a top-tier orchestrator by massive enterprises, they couldn't just build a walled garden that only supported their own hardware.
They had to play nice with the biggest kid on the playground.
Precisely. They had to deeply integrate with the incumbent heavyweight. Flashing firmware remotely is a highly vendor-specific, highly dangerous operation.
Because if it fails, you brick the switch.
Right. It requires validating checksums, ensuring there is enough flash memory available, transferring the massive image file, modifying the boot variables, and then safely initiating the reload. Supermicro likely built a dedicated integration module leveraging Arista's eAPI simply because it was robust enough to handle that complex remote firmware orchestration reliably.
So it's actually SCC flexing its capability as a true hyper-converged manager rather than just a proprietary management tool.
That's exactly how I read it.
It's fascinating. And for the times when the graphical interface isn't enough, or maybe you're dealing with a switch that isn't fully integrated into the GUI for updates, the manual includes a fallback. It mentions SSH forwarding integration.
A very useful feature.
Yeah, it allows the administrator to pull IP addresses and specific ports directly from SCC, and the manual uses port 23722 as an example. You can copy that and use it directly in terminal emulators like Putway.
And the inclusion of a non-standard port, like 237.282 in the manual's example, is very telling about how SCC is deployed.
Yeah, break that down for us. Why not just use the standard SSH port 22? Why this random 5-digit port?
Well, in a secure data center, you absolutely do not expose the management interfaces of your core switches directly to the corporate network.
Right.
And you certainly never expose them to the internet. You place them on a highly isolated, out-of-band management network.
So it's a completely separate physical network just for managing the devices.
Yes, exactly. To reach them, an administrator usually has to VPN in, then SSH into a heavily monitored jump server or bastion host, and then from there connect to the actual switch. It's tedious.
Lots of hops.
Too many hops. What SCC is doing here is acting as that secure proxy. By giving you a dynamic high-number port like 237.22, SCC has dynamically opened a secure temporary tunnel through its own proxy engine directly to the internal management port of that specific switch.
Oh, so you don't have to do the manual hops.
Right. You just point pre-TUI at the SCC server on that random port, and the orchestrator seamlessly forwards your keystrokes straight to the target device.
It completely abstracts the complexity of the out-of-band routing. It saves the engineer from having to look up jump server credentials, figure out the internal IP of the switch, and manually build an SSH tunnel. It just hands you the exact string you need to get to the command line instantly.
It's a huge time saver. And honestly, it's an acknowledgement from Supermicro that no matter how good your single pane of glass GUI is, sometimes a network engineer just needs to get their hands dirty in the raw CLI.
Right, to debug a complex routing protocol state that just isn't mapped to a pretty GUI widget yet.
Exactly. Sometimes you just need the command line.
And debugging is exactly where the final section of this user guide takes us. We've talked about how SCC pushes configurations, how it manages those delicate storage lanes, and how it handles firmware and CLI access. But how does the orchestrator and the network itself actually map its own topography in real time?
The visibility aspect.
Yeah. The manual outlines two distinct protocols for neighborly relations, LLDP and the M&E address table.
And these are truly the two foundational pillars of Layer 2 network visibility.
Okay, let's start with the first one. The documentation states that LLDP, which stands for Link Layer Discovery Protocol, provides the identity, capabilities, and neighbors of adjacent connected devices on the SCC fabric.
Right.
Now, I initially thought about this like people at a networking event handing out business cards. Like, hi, I'm Switch A, I'm a router, here is my capability. But earlier we talked about how row CE storage traffic is hypersensitive to overhead, to the point where even a dropped packet is catastrophic.
Yes.
So how does LLDP function constantly in the background without eating up valuable bandwidth and causing latency?
It works because LLDP is an incredibly lightweight, heavily localized protocol. It operates strictly at Layer 2. A switch doesn't route an LLDP frame across the entire network to every other device.
No, it doesn't.
No. It simply multicasts it out of its immediate physical ports, and the frame only goes to the device sitting at the exact other end of that specific physical cable.
Just one hop.
Exactly one hop. And the frames themselves are tiny. They are constructed using TLV's type, length, value fields. A switch simply packages its chassis ID, its port ID, and its system name into a tiny TLV frame, sends it across the short wire, and the receiving switch just stores that data in its local management information base.
So it's essentially an automated, proactive wire mapping tool. SCC can query the switch's LLDP database via an API, and it can instantly draw a highly accurate graphical topology map, because every switch knows exactly who is plugged into port 1 versus port 48.
Exactly. It completely eliminates the need for humans to manually trace cables.
Mm-hmm.
But, and this is the big, but LLDP only tells you what the infrastructure claims is physically plugged in.
Okay, what do you mean?
It tells you the physical intent. It does not tell you where the actual data is dynamically flowing at this very second.
And that distinction is where the guide introduces the MAC address table, or the CAM table. The manual specifies that the switch dynamically builds this table using the source MAC address of received frames to efficiently switch traffic.
And the CAM table content addressable memory is the beating heart of an Ethernet switch.
Okay, I originally visualized this like a bouncer at a club, right? The bouncer watches people walk in, checks their ID, and memorizes exactly who is in which room of the building.
It's a decent starting analogy.
Right, but if we are talking about a massive data center switch pushing terabytes of data per second, a human bouncer analogy completely breaks down. The switch isn't checking one ID at a time at the door. It's processing millions of frames a second. How does the CAM table dynamically build itself at that insane speed?
This is where we get into the literal physical silicon of the switch, the ASIC.
Okay, break that down for us.
Standard RAM, random access memory, is relatively slow for this. In standard RAM, you give the memory an address, and it returns the data stored at that address.
Right.
CAM, content addressable memory, works in exact reverse. You input the data, in this case a 48-bit AMM address, and the CAM instantly returns the physical port number where that address is located. And it does this lookup in parallel across the entire memory bank in a single microscopic clock cycle.
Oh, wow. So when a server sends a packet into, say, port 5, the switch ASIC rips open the Ethernet header in hardware, looks at the source M address, and instantly writes a record in the CAM table saying, this specific MC address lives down port 5.
Yes. And it does that for every single frame. And then simultaneously looks at the destination M address on that same packet, does a reverse lookup in the CAM table to find out which port that destination lives on, and switches the frame out that specific port.
All at the speed of light.
Basically, yes.
Yeah.
It's all done in hardware silicon, not software.
Which brings us to a specific troubleshooting tip in the manual that kind of confused me at first. It explicitly warns that administrators must use the refresh option in the UI periodically because the table changes based on network topology variances. It also includes a drop-down to sort these M addresses by specific VLAN numbers.
Right.
But if the CAM table is processed in silicon at the speed of light, why does the human administrator have to manually click a refresh button on the SCC dashboard? Shouldn't the dashboard just be live?
It's a great question. The reason is that the SCC dashboard isn't the switch. The dashboard is pulling a snapshot of that silicon memory over a management API. And in a modern data center, network topology variances happen constantly. They happen much faster than you'd want to pull an API. Consider a VMware cluster, for example.
I know, virtual machines.
Right. You have a virtual machine running on a physical server, and that server is plugged into switch A. That VM has a specific virtual MAC address. The CAM table on switch A sees the traffic and knows the VM is on port 10.
Okay, so the table is accurate.
But then an automated load balancer decides that server is running too hot or it's out of memory, so it triggers a VMO.
The live migration?
Exactly. The VM is migrated live, without dropping a connection, across the data center to a totally new physical server plugged into switch B.
So the VM physically moves across the building, but its MAC address stays exactly the same so the applications don't break.
Exactly. The instant that VM boots up on the new server, it sends out a gratuitous ARP, which is basically a broadcast frame announcing its presence to the new switch.
Saying, hey, I'm over here now.
Right. Switch B sees that frame, instantly updates its local CAM table, and the network converges. The traffic flows to the new location.
But let me guess, your SCC dashboard, which you loaded 5 minutes ago while sipping your espresso, still shows the old API snapshot.
Exactly. The dashboard still thinks the VM is on switch A.
Ah, so the refresh button isn't forcing the hardware to learn. It's forcing the SCC software to fetch the new reality from the hardware.
You hit the nail on the head. If you are a network admin trying to track down a rogue device or figure out why an application suddenly dropped offline after a vMotion migration, filtering that CAM table by VLAN and constantly refreshing is your absolute ground truth.
It's the ultimate detective tool.
It really is.
Yeah.
LLDP tells you where the physical cables go. The JSON build plan tells you the intended theoretical design. But the CAM table tells you the irrefutable cryptographic reality of where the data is actually originating right this exact second.
That triangulated visibility comparing intent, physical layout, and real-time flow, that is the entire value proposition of a tool like SuperCloud Composer, isn't it? It allows a single operator to correlate all three realities.
And that's the only way to manage environments this large without losing your mind.
We have dissected a massive amount of architecture today. I mean, from the orchestrator parsing JSON build plans and pushing multi-threaded API calls to the switch sweeper relentlessly policing configuration drift in the middle of the night.
It's a lot to take in.
It really is. We explored how priority-based flow control and ETS manipulate buffer queues to create perfectly lossless environments for highly sensitive NVMe storage fabrics. We broke down the UI constraints for crash cart operators freezing in the cold aisle, the dangers of firmware flashing, and that weird Arista eAPI integration. And finally, the silicon-level mechanics of LLDP and dynamic CAM table hashing.
When you step back and look at the totality of these systems working together, you realize that managing infrastructure at this scale is basically an ongoing, endless war between entropy and orchestration.
Yeah, that tension is palpable throughout the entire manual. You have the rigid, automated rules of the JSON build plan trying to lock the environment down perfectly. But on the other side, the system is fundamentally designed to be fluid, dynamically learning MC addresses, utilizing volatile memory for running configs, supporting real-time VM migrations across the building.
Has to be both.
Right. If the architecture was purely rigid, a single moved cable or a single failed port would shatter the network. If it was purely dynamic, you would have zero security, massive routing loops, and untraceable drift.
Which actually leads to a really fascinating thought experiment regarding the future of platforms like SCC.
Oh, what are you thinking?
Well, currently, the switch sweeper enforces compliance by checking the dynamic memory against the human-authored JSON blueprint, right?
Right, checking if someone changed the load-bearing wall.
Exactly. It assumes the human architect who wrote the JSON was right and the drift is wrong. But we also just established that the CAM table and the hardware are constantly learning the actual optimal reality of the network flow in real time.
Okay, where are you taking this?
If the orchestrator already has access to real-time telemetry, LLDP physical topology mapping, and CAM table traffic flows, how long until it simply stops relying on humans to author the JSON build plans in the first place?
Wait, you mean the software writing its own rules?
Yeah, we are rapidly approaching a paradigm where an AI engine within an orchestrator like SCC observes the massive traffic patterns, recognizes that the human's desired state in the JSON file is actually inefficient, and autonomously rewrites the blueprints to dynamically optimize the physical queuing and routing protocols on the fly.
Wow, so the blueprint essentially writes itself based on the real-time physics of the data flow.
Yes, the switch sweeper transitions from being just a compliance building inspector into becoming an autonomous architect.
That is wild to think about. A completely self-healing, self-optimizing infrastructure. It fundamentally changes how we view these massive data centers.
It does. We're getting closer to it every day.
So to you listening, the next time you are standing outside one of those massive, windowless concrete data center buildings, remember that the true architecture isn't the physical steel or the giant cooling towers. The real structure is a volatile, invisible matrix of lossless queues, dynamic memory tables, and continuous API reconciliation, all operating at the speed of light to keep our digital world from collapsing. Keep digging into these manuals, keep questioning the complex systems around you, and stay curious. We will see you on the next deep dive.